Good afternoon. As David said yesterday, it's hard being the last speaker. I'm sure you guys are tired. I'm exhausted. It's 3 a.m. in my head right now, but let's get through this. So my slides are not created in MS Paint. I wish I would have done that. I didn't have enough time to do it last night, but maybe next time. A little bit about me. I'm an engineer at Eyesight Partners. I've been there for 3.5 years. Prior to that, I worked at the MITRE Corporation. You may be familiar with MITRE. They do CVE. Prior to MITRE, I did some work for defense contractors and then the U.S. military for that. My primary tasks at work are reverse engineering malware, looking at security patches, and just random tasks. Some of you may have heard of me before, but you're actually probably thinking of this other guy that wrote The Art of Exploitation. This is not me. If you brought your copy of your book for me to sign, I will sign it for you, though. Yes. Just briefly, Eyesight Partners is a threat intelligence provider. If you're interested, please visit our website or come speak to me after this talk or tonight. Today, we are going to be talking about application compatibility. I'm going to define that, and I'm going to discuss some tools that you can use to analyze and create your own. Talk about different prior works out there. And talk about Microsoft's EMIT, and go over some real-world examples where malware is using these techniques today. So application compatibility is something that Microsoft introduced in Windows XP, and it's to address compatibility issues from going from Windows 2000 and NT to XP and XP to Win 7, etc. It covers many different issues. One simple example of this is if you consider going from XP to Windows 7, if you've got an application that's been compiled with hard-coded file paths. So if you have C:documents and settings, that would be for XP, and on Windows 7, it would be C:users. So if you've got a programmer that's developed code for Windows XP and you try to just run that on your Windows 7 box, it's not going to work. So Microsoft has invented this application compatibility layer that sits between the operating system and a target application that could intercept lots of different function calls and provide a mechanism for you to fix these problems without recompiling the code to work for these upgraded platforms. Microsoft has a whole website dedicated to Fix-Its. If you go read their documentation, this is kind of a snippet of the words that they have to describe it for graphical issues, file system issues, registry issues, etc. And the big word on the page over and over again is failure. So whenever there's a failure case, they have a Fix-It for that. There's thousands of them. I think they call it the Microsoft Fix-It Center. Here's an example of a game I've never played before, but I came across its fix when I was doing my research. And when you play this game, and I guess if it's an older game and you bring it to Windows 7 or Vista, it will crash when you perform an Alt-Tab. And so either the creators of this game or a big fan of this game created a Microsoft Fix-It to address this. And the particular shim that they used here was something called forced direct draw emulation. And the purpose of this is just to force the direct draw function into some emulation mode. I don't really understand it. It's not important. But there are like hundreds and hundreds of different shims, and these guys had some random graphics crash when doing Alt-Tab, so there's a fix for that. So let's get into some tools that you can use to look at these. 5. Microsoft has the Application Compatibility Toolkit, SDB to XML, which is actually from a Microsoft employee. CDD is Alex Ionescu. SDB Inst is a command line utility from Microsoft. And SDB Explorer is a tool that I created during my research. And unfortunately, I named it SDB Explorer, which if you Google that, you'll find lots of hits for Amazon's simple database. So where SDB in this case stands for Shim database, Amazon has way more hits than me for simple database. So it's kind of hard to find. So here's a screenshot of Microsoft's Application Compatibility Toolkit. This is freely available. They provide documentation on how to use it. It's not great. It's fairly limited, but they do provide information on how administrators can go ahead and you can create your own compatibility fixes for different products. I've got 2 examples here that I've created myself. Both are targeting Internet Explorer. And the picture on the left is for a compatibility fix called Shim via EAT, which means it's going to provide a method to hook functions via an export address table. On the right is a compatibility mode called Elevate Create Process. So therefore, it will elevate to administrator privileges. One important thing to get out of this slide here is the thing below those is this matching files. So it says matching files, iexplore.exe, and then there's several categories where it says bin file version, product name, company name. When this layer that's between the operating system and the application that's being run, that layer is what reads these SDB files, and it has to make sure that the criteria has been met before it applies this fix. So when it reads this SDB file, say for the left one, if it's this particular version of Internet Explorer, then it's going to apply this Shim via EAT fix. Next is a tool created by a Microsoft employee called SDB to XML. And the name says what it does. It takes a Shim database file and converts that binary file into an XML blob. I've got some lines on here that say it does not parse in-memory fixits and it cannot dump patch bits information. That is related to a previous talk I did this year, which was solely focused on the in-memory patching features of this compatibility framework. That patch bits information is basically that big blob of base64 on the top. And that blob is what actually got me started in this, trying to figure out what is that, what does it do, and how can I analyze that. CDD, Alex Ionescu. These are the command line options that are available. Unfortunately, this tool was never released, but he's got screenshots of it, being used for showing shims and executables and patches. I was most interested in his option for showing patches, but it was never released. So a tool for installing SDB files is a command line utility that is on your Windows boxes right now called SDB Inst. And you just pass it a SDB file name. And one thing to note is that it requires administrator privileges. And the reason it does will be more apparent on the next slide. I'll get into that. But I can't remember if I just said this. Sorry. I'm so tired. The screenshot in the bottom is a side effect of this program. When you install SDB files through this mechanism, they will show up in the Add Remove Programs dialog box. So in this case, I've installed 2 fixits that fix or prevent exploitation of these two particular CVEs. And so they show up in the add and remove programs dialog box. So the reason that you have to be administrator to run that tool is because it needs to be able to write to HKey local machine and these Windows directory paths. And those require administrator. So that shim layer will first look at this top registry key, appcompat flags custom. There will be a list of keys. Each key will be a name of an executable. So you might find iexplore.exe under there. You might find winward.exe, firefox.exe, etc. If there's an associated entry in there, you then grab a GUID from there, and then you match that to this other path here, this appcompat flags installed STBs. If there's a GUID there, then you get this picture that I have on the bottom. This is for the CVE 2012-1889. This was released by Microsoft. You can see that it has the database timestamp when I installed it. The database path is the full path to where this file with this .stb extension exists on my hard drive. And the default file locations I've listed here: appatch custom and appatch custom 64. These are just default for the stb inst tool that I've been talking about. It's not a requirement that they are in that location, just by convention. So when I was starting my research, I looking into how this worked, and I decided to add this feature of installing or registering STB files. And so if you register them through STB Explorer, it does not have the side effect of showing up in add and remove programs, and it does not copy these STB files to the default locations. So then if you do that, you have to be aware that if you're dealing with 64-bit patches, the path, somewhere in the path needs to be the word custom 64. And my program is not immune to the administrator privileges required anyway, so either way you need to be administrator rights to be able to register, install these files. So continue on to some prior work. I'm going to talk about these particular items: Alex INSU's blog series, Mark Baggett's presentation at Derbycon, my previous talk I did this year at Black Hat Asia and Syscan 360, and Chris Graham's blog post. So first, Alex INSU released this blog series. It was supposed to be 9 parts. He didn't get to 9. He stopped after 4, unfortunately. Or fortunately for me, if he would have finished, I probably would have never got started in this topic to begin with. So I guess that's good for me. I'm going to be talking about the ones I've highlighted in red. System shims, which he considers the most interesting. And I was also interested in the runtime in-memory patching. And that was the whole focus of my previous talk. So the system shims can be found in this directory. Sysmain.stb, drivermain.stb, msimain, and pcamin. I'm going to be talking about this first one. So if you use STB Explorer or if you use STB to XML, either way you'll get the same type of output. But my particular program, I passed this -t option that basically prints a tree view of the STB file. In this particular example, I'm showing the show window IE shim and the shrinker shim. And I first saw these names, I had no idea what they meant, as I doubt anyone here knows that. And so where do you go to find the information out? There's actually this thing I've highlighted in the red box. It's the description resource ID. So we can go find that resource ID to get the description of this particular thing. So on the Japanese side, that's your path. It's appatch/JP, that particular MUI file. And on the English side, it's ACRES DLL MUI. So these two resources, if you go into the string table, you'll find these. The show window API, in this case, is just used for fixing problems due to some tabs. I don't really understand that fully. That's not the point. And the second one here is that the shrinker was related to the shrinker resource compression library. But this is just a method for you to be able to figure out the descriptions of the shims if you're not familiar with them when you're performing your own research in this area. Mark Baggett presented at Derbycon, Windows owned by default. And his focus was taking a look at the application compatibility framework from the point of view of an attacker, and he's interested in doing rootkit type behaviors like process execution redirection, API hooking, hiding in the file system, hiding in the registry, disabling security features such as DEP and ASLR, and executing backdoors. So he took a look at that whole long list of shims that are available to use, and he said, which of these can I use as an attacker to perform my duties? And so one he saw right away was inject DLL. And if you take this resource ID and go get the description as we just saw how to do, you'll find that basically it's a fix for programs that require a DLO to be loaded, but there wasn't a previous call to a load library. And so this shim will take care of loading this library for you before the process starts. So to figure out how these shims work or what they actually do, how they're implemented, underneath the name is inject DLL. Underneath it is DLL file, acgeneral.dll. If you bring that into IDA, you can go look for this NSInjectDLL notify FN method. And if you look in there, it's literally just a call to load library. So all an attacker has to do is create a DLL with their code in DLL main and tell the inject DLL shim that it should load the DLL of this one. Then you've got code exec in a process very easily. Second one he talked about was redirect exe. And again, this is backed and implemented in the AC general DLL. And if you look at that, it will just do a create process, close the handles to that process, and then exit itself. So let's say you're going to redirect calc to notepad. So you double-click calculator, calculator starts to come up, the Windows loader is doing this process of loading it into memory. It says, okay, I need to apply a shim because someone has registered or installed a shim for calculator. And so it starts up before the Windows main hits in calculator. It does a create process for notepad, so then notepad starts up, and then calc is terminated. And that's how a redirect works. This could be useful, and you'll see it is very useful later for attackers. Other ones he talked about was registry virtualization. So say you wanted to hide something in the registry, you could create a shim for regedit so that if someone is going to look for a specific key value within looking through the registry editor, it'll actually redirect to a different location in the registry to a place that doesn't exist or might contain false information. Different tricks like that. All right. So this is about my talk, which was mainly about the in-memory patch structure. And so like I said before, part of my job is performing diff analysis of patches, and I'm mostly concerned about looking for security-related changes. And so this is an example of, I was doing a bin diff for 2 different versions of MS HTML DLL. And bin diff identified 465 different matched functions, which means there's 465 places I need to go look at and figure out, is that a security-related change, or is that just a compiler optimization where they've changed, they're using EBX versus ECX, or is it something, more severe? So it's a very long process. It can be fun. It can be awful. But if Microsoft releases a fix-it in-memory patch for this particular CVE that I've listed here, there was 2 changes. There was basically 4 bytes that changed total, 4 bytes which relate to changing some opcodes. And so for me doing, patch analysis, it's much easier to look at 2 things than 465 things. And that's what was my initial motivation in getting started in this topic. So this in-memory patch feature has been in Windows since XP, and I've only found 5 cases where they've used the in-memory patch feature. It's not documented at all. I've documented it in my previous work, but other than that, it's not. Today I'm going to be talking about this CVE 2014-4114 and its related CVE that was for the bypass. Some people call it OLE packager vulnerability. My previous work, I talked about the second CVE listed, which was an IE use after free vulnerability. So kind of a quick background of how this OLE packager vulnerability works. There's a PowerPoint lure. They somehow convince you that you need to open this PowerPoint because it's got good stuff in it. And within that PowerPoint is an evil INF that's packaged in with a packager object. Then somehow this INF file, someone right-clicks, they click install, and this INF default installer program runs and uses this user-controlled evil.inf file to execute code. So how does this work? So first, PowerPoint says, okay, someone's embedded a packager object in this PowerPoint, so it needs to load the packager DLL into the process memory space. At that point, the packager DLL is responsible for copying that INF file into the temp folder. Then there's a PowerPoint animation, and this invokes a do-verb command. This do-verb command is associated with doing a right-click context menu for an INF file. And so the right-click do-verb action was actually to do the second one in the list, which is to do an install. When you right-click INF and click install, it launches INF default install and uses that user-controlled INF file. And at that point, you've got code execution because it's running the attacker's code. So Microsoft fixed this October 2014. What they did was they took care of this first thing that I've highlighted here in red. When it copies the evil.inf file into the temp folder, they've set a metadata flag on that file. They said mark file unsafe. So later on in this chain of events, when the INF default install program starts up, one of its jobs is to say, hey, I need to make sure that any INF files that I'm going to be handling need to be safe. So it by default checks, is there an unsafe flag set on that INF file? In this case, there is an unsafe flag, and therefore it's going to prompt the user. So here we can see that same path of events, and now it's prompting me open file security warning. Are you sure you really want to do this? And I'm going to say no. Okay. Shortly after the patch, there was a bypass. Very quickly, Hai-Fei Li was blogging about that he found a bypass and he's notified Microsoft. And then Google found exploitation in the wild of a bypass. So the way they worked was Google found that someone embedded a exe instead of an INF file. And when they did the right-click action, they did the right-click action for run as administrator. That action causes a UAC prompt. And if the user clicks yes, you've got code execution, and it's running in a higher privilege. But that's kind of obvious that something bad might be happening, so maybe it's not as reliable. Hai-Fei Li found that if someone has installed a Python on their system, and you embed a Python file in a PowerPoint, the right-click context menu for that, the second one is edit with idle. And when that editor starts up, part of its job is to look in that same directory where that Python file exists, and it looks for files with a specific file name. And if those files are there, you've got code exec running within that Python process. And so instead of embedding just evil.py, Hai-Fei Li seeded that temp folder with file names that he could control the names, put in that temp folder, then put evil.py, right-click, code exec. So shortly thereafter, Microsoft released a Fix-It. This is a snippet of the output from STB Explorer viewing the STB file that they released. I've got highlighted here in bold this showing the matching file entries. In this particular case, it's looking for packager.dll. So when PowerPoint starts, this doesn't actually do anything. It waits until packager.dll has been loaded into the PowerPoint process's memory space. If it does that, then it's going to apply this patch ref. That patch ref, I'll explain where this information comes from shortly. But this patch ref is for the following things. It's going to first look at a particular relative virtual address in the packager.dll. In this case, it's looking for a call instruction. And it's going to replace it with CC bytes for software breakpoint. So as Ilfek said this morning, this is a great disassembler, but without symbols, it's kind of useless. What is that call doing? So if we bring packager into IDA and look at it, we can see that the particular call that they are patching out was the call to get context menu. And they have replaced it with this software breakpoint. So now if you've got this installed and you were to double-click one of these evil PowerPoints, instead of it doing the right-click context menu, it's going to do the software breakpoint, which if you're not in a debugger, it's just going to terminate the process. So the real fix happened in November, and what they've done now is this, every time you go to do a do verb right-click context menu, it's now going to prompt the user. And so the package you are about to open will run a program contained in the package. That program can do anything. It may harm your computer. Unless you are absolutely certain about the nature, source, press cancel. So I read that and I say, okay, I'm going to press cancel. But some users just like to click OK. So, okay. So how do I figure out that the information that I had before? I just showed you it's going to do a look for these call instruction, and then it's going to replace that with CC bytes. I had to write my own tool to do that because none of the existing tools out there provided any information on in-memory patches. So for example, if you take one of the STB files associated with this CVE here, which is 0322. It targets Internet Explorer, and it's got matching file entries for specific versions. So this bin file version is for IE10 with this particular PE checksum. And then if that matches, what happens? It doesn't. There's nothing here. There's no compatibility fix. There's no compatibility mode. So what the heck does this thing do? Not very helpful. And on the same matching files concept, I added an option to STB Explorer. You give a -D option, and that will show you all of essentially the targets for the patch. So it's gonna go through those matching file entries and show you which particular DLLs it's going to go after. So in this case, for this 6253, the fix-it is going to target if that particular version and checksum of packager.dll is loaded. And so if you don't have those particular versions and you've got the shim installed, it's pretty much useless. I showed that similar output before, but with -T. Prints the tree for this particular PowerPoint, and what you see here is that it's got the matching file entries. At the bottom, it has this this patch tag ID. It's number 746, and so that's got me interested. What is 746? And in the left-hand column of all these rows, that's actually a tag ID, and a tag ID is also the offset within the file. So if you wanted to play around with STB files and bring them into a hex editor, that number relates to where it exists in the file, and it also happens to be the tag ID. So when I say patch tag ID 746 or in hex 2EA, that's where you need to go look for that, where that patch is at. When you run STB to XML, the tool from the Microsoft employee, here again you see 746, but if you take the whole output that they provided, nowhere do you see the number 746. So I needed something to create the linkage. This tag ID is related to this patch section within the same STB file. And so I did that. Here is an example. The top part is for a patch entry. You can see that it starts with 2EA, and then there's an associated patch bits section. Down at the bottom, you have a PE checksum, a patch reference, and a patch tag ID. All these things I've highlighted in the red box are different ways that you can use, that you can pass to my program to print out the patch details for you. So here, in this next slide, I'm passing the ID to EA, and I'm giving the -P option. And then this will print out the details for that particular version that I've specified. And we see the same output that we saw before. It's going to do a match opcode at a specific RVA within the packager.dll for those 5 bytes, and then do a replacement with those 5 bytes. Like I said before, it's not very useful without symbols. So I added a -I option, and this instead will print out a IDA Python script for you. So then it's your job to go get the particular DLL that you want. You load it into IDA, you print out the associated script that you want, and then you can take this and just copy and paste it right into the IDA script window. So this is kind of a summary of my previous talk. I explained all the features of the STB Explorer tool that I wrote. I explained in very, very detailed the in-memory patch file format and how I went down the path of figuring it all out. There's lots of pictures of hex dumps, etc. If you're interested, you can find this talk on YouTube. Just search my name and Black Hat, you'll find it. I showed how to analyze these fixes. I kind of showed you that today as well. And what I didn't show you today is there's no tool out there besides mine that allows you to create your own in-memory patches. And so I created a mechanism where you can create a config file where you specify the program name, the module that you want to target, the RVAs that you want to target, the bytes that you want to search for, the bytes that you want to replace. You'll take that information and it will spit out a .stb file for you that you can then go register. All right, moving on to Chris Graham, shimming your way past UAC. So Windows has signed files with what's called an auto-elevate permission. An example of this is soundvolume.exe. So I think early on, Microsoft figured out that people are getting annoyed by a UAC prompt happening all the time. So every time you want to go change your volume, there'd be a UAC prompt, another UAC prompt. And so Microsoft created this auto-elevate permission. And they say, okay, well, I know sound volume is safe, and I automatically want it to elevate to administrator privileges. So Chris noticed this and said, okay, well, if I use the redirect exe shim type, maybe I can redirect an elevated process and then have my own process be elevated. And that's exactly what happens. So you create a shim for sound volume that does a redirect exe to evil exe. You register it using either stb inst or some other mechanism, and you start sound volume. So sound volume is being started by the Windows loader. The Windows loader says, okay, I need to elevate it. So it elevates it, and then it says, okay, well, there's a shim I need to apply, and it applies the shim. And the shim says, okay, do a create process to evil. Evil's now elevated, and then sound volume goes away. So one other note is that he lists a whole list of processes that have this auto-elevate permission. The stb inst tool by Microsoft has this auto-elevate permission. So you can install shims using stb inst, and it will auto-elevate. So as long as the user has the ability to become administrator, it will automatically do that without prompting the user. All right, let's talk a little bit about emit. Microsoft's Enhanced Mitigation Experience Toolkit, I believe the current version is 5.1, provides a whole suite of features. It enables DEP, does mandatory ASLR, does some filtering and drop detection, etc. And it's not that your whole system is protected when you run emit. There's a specific list of processes that it actually works for. And for each of those processes, you could enable and disable these features. And so emit is actually run through this shim engine, this application compatibility framework. And the same directory here, this app patch, is where we had our system shims that we talked about very early on with Alex Ionescu's work. Here, Microsoft has created their own emit.dll and placed it in this app patch directory, and there's an associated 64-bit version there as well. And so if you looked in the registry at the locations we talked about before, for like, say, Internet Explorer, which has been protected, you'll find this entry, and it says the database is for emit, and this is where the file on disk exists. So if we go look at that stb file using stb Explorer, on the bottom, I'm showing Adobe Reader, And there's a matching files entry for asterisk. So it doesn't care what version of Adobe Reader, it doesn't care PE checksum, it's just going to match based on that name. And if it matches, it's going to apply this particular shim where the name is emit shim and the tag ID is 2F8. And there is 2F8, the name again, and the DLL is emit64.dll. So let's say I double click Adobe Reader. Windows Loader starts it up and says, okay, there's a shim I need to apply. And it says, okay, well, I actually need to load emit64. And so it loads emit64.dll into the Adobe Reader process. And then that DLL is responsible for determining or enforcing the features that have been enabled or disabled for that particular process. And one thing to note is that I'll talk about that in a minute. Let's talk about a couple real-world examples. Okay, Search Protect, Black Energy, and Farfly. So Search Protect, potentially unwanted program, adware. I've never actually used this because I don't like adware, but I've heard that it gives you lots of advertisements and maybe modifies your search terms. This is actually, I saw using application compatibility to persist. So it's not like this program has a monitor process that's constantly looking for, did you kill the malware to restart itself. This is actually using the application compatibility framework to persist. So it utilizes the inject DLL shim, and it registers it for Internet Explorer and Firefox. So if you double click IE starts, Windows says, oh, okay, there's a shim I need to apply. And it does an inject DLL with the Search Protect library right into the IE process. So every time you start IE or Firefox, it loads this DLL. That DLL hooks some functions, provides additional features for you. And it's currently doing it in a way that malware hasn't traditionally done it in the past. One thing to know about the inject DLL is as far as I know, it only works for 32-bit processes. So if you're targeting 64-bit processes, I don't think that's going to work for you. Next, Black Energy. This is information taken from F-Secure white paper on Black Energy, where they say that it's been recently targeting the Ukrainian government. And they used a UAC bypass technique. It's the same exact technique that Chris Graham documented. And I'm not sure exactly which one happened first, if Black Energy did it and then Chris saw it and then talked about it, or if Chris published this blog and the Black Energy authors figured it out and decided to use it. They also mention in the paper that they did a driver signing bypass, and my first initial thought was that they were using Shims to do this, but I talked with Anton, I'll mention it here in a minute, and he said that's not the case. Basically, to do their driver signing bypass, it's possible to put your computer into developer mode, and then you have the ability to load unsigned drivers. But a side effect of being in developer mode is they provide this notification on the bottom left-hand side of your screen saying that you are in developer mode. And obviously, a user might be confused by that and might think something's up. So the authors of this malware knew that the string that says developer mode is just in a resource file. And so they went to that resource file for every language and patched out that string with null bytes. So Anton, who's sitting over there from ESAT, reported 0 nights in November. about this variant of Farfly. And he showed that the malware itself dropped 2 files into the Windows app patch directory, one of which is called acprotect.dll. Then it also dropped a shim database file into the app patch custom directory and registered it. If we take a look at the FTP file using FTP Explorer, we can see that there's actually 2 processes names that are listed here, swung32.exe and explore.exe. The first one, you can see that, again, it's got that matching files asterisk. So as long as the process name matches, it's going to apply this particular shim. And then this shim is listed as acprotect.dll. And so this is the same exact style that we just talked about with emit. It's how emit works. And the advantage of this technique over inject DLL is we saw that emit worked for both 32-bit and 64-bit processes. So you could provide in this case, an AC protect for a 32-bit version of it, and you can provide a 64-bit version of it. And then you have a STB file which will, one for 32-bit, one for 64-bit, and it will, magically just work for either one. So this all sounds bad. What should we do about it? It's possible to disable the shim engine. I don't recommend this, though. It's going to break emit. And one note is like all the things we've talked about today are all through application compatibility. So if you disable this, you disable the good, and you disable the bad. So I think there's better gains from having it in your system. So I don't recommend disabling it. If you did want to disable it, I provide the path there to do that through the group policy editor. And so I think everyone should be, use the knowledge you gain here, be aware of this technique out there. And like I said, all these different techniques I talked about today all require on those 2 registry entries that I mentioned early on in the talk. So you can go search there, is something there that shouldn't be, and you can further investigate from that path. The sysinternals tool auto runs does not currently consider application compatibility fixes as a method for persistence for attackers, but they're working on it. I spoke with Mark and he emailed me back and said, wow, I'm shocked this didn't happen 5 years ago. And he said he'll try to get something together in a couple months. I think that Microsoft should add signature support, or add signatures to STB files, so that if I run Internet Explorer and the Windows OS is about to inject a DLL or run a shim that's supposed to provide some additional features to my browser, I want to be aware of that. But I only want to be aware of it if it's something that Microsoft didn't produce. I think that should be doable. So this is a new method attackers are using today. This is not a vulnerability. This is not really an exploit. They're just exploiting a feature. And this feature that has been in Windows since Windows XP. And defenders should for sure start looking for this on your computers. And again, the STB files require administrator privileges to install. So restrict your users so that they can't auto-elevate. And require the attackers have to first do some type of elevation of privilege attack to be able to install these STB files. Here are some references that I used. I'd like to thank my family, friends, and definitely the CodeBlue staff. And before questions, I'll quote Dave from yesterday. I'm ready to party. So the source code for SB Explorer is on GitHub. I plan on updating it soon. I had no idea anyone actually was aware of it or used it. And I spoke with Anton, and he used it, and he told me a couple bugs in it. I was like, oh, I wasn't aware anyone was actually using my code. So if you have any questions, comments about it, please let me know so I can maintain it. Otherwise, it's just going to sit there and do nothing. So I will be fixing the bugs he's disclosed to me and provide some updates when I have time. So here's my email. I can take questions over email right here or tonight. It's up to you.
Is there any reason why there is no authentication in the SDB files other than administrator, but like in my presentation, assume it's okay? Are other companies using these files to fix, or is just a Microsoft thing and they are not doing code signing because they didn't thought about this?
So why Microsoft chose not to add some type of authentication, I don't know. Can you comment on that?
Is there anyone using this for normal patches? Because it's a very powerful tool for doing temporary patches to fix temporary stuff.
I haven't seen many examples. Besides, there's a few games out there that use these for sure. But I do think this might be a good mechanism for maybe antivirus vendors to inject code into processes or different for debugging purposes. But there's not a lot of people out there talking about it right now.